Hello and welcome to the final night of Advent of Code. It's Christmas Eve here, and everyone's very excited for Christmas Day, and I'm very excited for the last problem. About 15 seconds to go here. Let's make sure Eclipse is doing good. Oh yeah, doing quite well. Yeah, yesterday's problem was a fun one. Let's see what they've got for us tonight. CPU garbage collector. We're doomed, it says. Turing machine blueprints. Okay. Uh-huh. Performa, okay. All right, a Turing machine. We can make one of those. Can confirm by taking a diagnostic checksum. All right, here's the puzzle input. Interesting. Okay. Well, I think I can write a Turing machine. So let's see. State of a Turing machine is defined by, let's see, the code, the tape, and your position on the tape. Oh, and then something that we'll call a state. And hopefully that doesn't get too confusing. As machine, like this. All right. So the code here is going to basically be a map from, let's call it, from a state. So a pair of, maybe we can do it like this. So A says that in state 0, 1, right, and B. And in 1, we have 0, left, C, like this. And then, let's see, so here, okay, C, D, E, F. All right, and then so we say, we write out the value 1, left A, 1, left D, 1, left D. And then we have 1, right D, 1, 0, so 0, right C. Okay. 0, left B. Zero, right E. 1, right C. 1, left F. And 1, left E. And 1, right A. Okay. So it'd be kind of nice to double check this. I wonder if I could do something like, I think I can do something like print like this using awk. So we have 1, right B, 0, left C, 1, left A, 1, left A, 1, 1, left D. It says for B. 1, left D, like this. Okay. And 1, right D. O right C, O left B, O right E, 1 right C, 1 left F, 1 left F, 1 left E, 1 right A. Oh, quite a few mistakes there. See how well this bodes. Okay. And then let's also have the number of steps taken already here. Actually, we're going to have this as an input. Okay. So what we do is we get in the code. Let's see. We have to, the first thing is going to be the current state. And then the next thing is going to be tape pause like this. Yeah, that seems fine. Okay. So then let write move state here, and then basically take the machine, assoc app soc in. No, let's see. So I think I can do this right. Yeah. Okay. So the tape is here. And then I want to, at this position, associate in that. Then update in, update the position. -1, right, +1 to the movement. And let's see, S for the state that we want to go into. Assoc 3, new state. All right, and the code doesn't change. All right. So perform a diagnostic checksum. All right, how do I do a checksum? Once the specified number, the Turing machine should pause, count the number of times 1 appears on the tape. Okay. So why don't we do something like reduce step starting with our code, an empty tape, position of 0. Let's see. Begins in state A, and then go over range. This should have this many steps. Then basically in this thing, we want to get tape, which is here. Actually, here, let's just define this to be the answer. All right. Here's our code, here's the step function. Null pointer exception where. So in update, yep, so this should just be 2. Okay. Another null pointer. Again in update. Oh, right, this should just be, no, this is right. Of course, this is actually supposed to be deck ink. Okay. All right, once again. All right, let's observe here. All right, so given an MM here, all right, so the very beginning, in our code a tape position. Oh, right. We default to 0. Okay. Then once we have our answer X, we're going to have to do something like get the second, number 2, number 1 thing out here. Filter on, it's got to be 1, and do a count like this. Get our answer. And actually, I think that we could probably work off just the current machine here and get a, oh, nope, there we go. Huh. Okay, so that doesn't seem right. How big is the tape? Okay. Interesting. Okay. All right, so we have tape positions here. Y, so we associate in at 1 and the position W. But the W should be should just be the thing that we wrote. Of course, the vowels here. Okay. Good answer, right? 129. And then we reboot the printer here. Here we go. All right. Great. That was a lot of fun. Let's take a look at the leaderboard for the day, just to see how far behind we were. So let's see. Looks like, oh, we were right in there. It's only 9:12 right now, but yeah. So yeah, maybe if we had made a few some fewer dumb mistakes, then we would have done better. This user, I imagine, had a had a Turing machine implementation already in like a library or something. If not, then very well done. Yeah. So I think I sort of skipped over the explanation a little bit, but you can, if you're not familiar with what a Turing machine is, then you can look it up. But basically, it's it's an abstraction of a computer with a memory and code. So it's basically saying that it's a particular machine that has a state, and then each step, what you do is you check the state that the machine is in, and then you check the value on the tape. And then based on that, you have the option of writing a new value to the tape and moving either to the left or to the right on the tape. And then you can stay in the same state, or you can move to the next one. Definitions of Turing machines also usually have a final state. They don't have to, just like you can write a program that never terminates. But so this one doesn't. For example, this one just sort of says that you can stop after this many steps. So okay, so this definition may seem kind of limited, but actually you can write any possible computer program in a Turing machine. So it's theorized that anything that we talk about when we talk about something being able to be computed can be computed by a Turing machine. It's equivalent to a lot of other formalisms for talking about machines. And they get complicated very, very quickly. So you can write programs in as Turing machines with a small number of states that just that run for unbelievably long lengths of time, um, and then terminate, which is pretty amazing, because you can write. I can write a small program that never terminates. I could write you know something like this. That's a small program that never terminates. But imagine writing like a program of similar length that would run for um, billions of steps in a definition like this. Uh, with like say just six states, for example. You can write Turing machines that run for um, large numbers of states and then terminate. So yeah, pretty incredible stuff. Um, as far as the implementation goes, it was pretty straightforward. I lost a little bit of time making sure that I got the code right. I could have written a parser. I realized a little bit too late, which was that if I just sort of I just copied this to my clipboard and used awk to print the last word on um, each line, then I can actually take this here, and it's a fairly straightforward transformation. On my other machine, I actually have a utility that can take sequences of lines here and um, basically tab separate every n of them. So yeah, I could probably have done something like that. Maybe removed all like the colons and the get rid of colons and dots, and there's basically, so I could pop it into Vim or something like this. So yeah, you could imagine basically having like this be the input to the program rather than me coding it all out. And that's a process, as you saw, that was a little bit fraught. But yeah, so that was an option. And then as far as a step went, yeah, the machine is just represented by its code, the tape, the position on the tape, and then the state that it's in. I avoided like index out of bounds, especially negative indexes, by representing the tape as a map rather than um, a vector, as might be a little bit more obvious. And then yeah, each step along the way. I mean, this is just definition of the machine. You want to grab, write the thing out to the tape, move your head, and then set yourself to the new state. So straightforward. Yeah, maybe incredible that just from this definition we have a sort of universal computer. But that's a Turing machine. So so yeah, this is the end of the Advent of Code 2017 series. Let's take a look at our calendar. Oh boy, what have we got up at the top here? Some kind of naughty. Nice. Okay. Huh. Huh. That's funny. Yeah, these are all these are all folks that are on my just on some private leaderboards. I wonder if it changes the when you refresh. Uh-huh. Okay, still the Easter Bunny. Okay, so yeah, it does change. Okay, well, very cool, very fun event. Like to thank Topaz who puts this on every year. It's a lot of work but we appreciate it. Um, and I'd like to thank my lovely wife Nancy and for encouraging me to do this and making our the lovely title cards for the series. Um, and that's it. If this is going on in Advent of 2018, then I'll be participating then too. So it was a lot of fun, and I learned a lot. So yeah, uh, thanks for watching. I hope you have a very Merry Christmas and Happy New Year, and enjoy your holidays. All right, thanks for watching.